Hey guys, welcome to Math 1 again. Today we're doing Chapter 3, Section 6. And today we are looking at our first section on symmetry. So let's get after it. Here we go. For a figure to have symmetry, there must be a, not even ready, here we go. There must be a transformation that maps the figure onto itself, or it leaves the figure unchanged. We will cover in this next couple times, we will cover 3 types of symmetry. Today we're only going to cover one, and today we are going to cover reflection symmetry. So here we go. A figure has reflection symmetry if there is a line of reflection called a line of symmetry that carries it onto itself. I kind of wish I'd put the word maps there. That maps it onto itself. Some figures have more than one line of symmetry. So we are looking for a line of reflection that when you use the line of reflection, it would map the figure onto itself. All right? And here I have a bunch of shapes, and what I would like you to try to do on your own is draw any lines that you think would be a line of symmetry. Like if you took the shape and you folded it on that line, each half would match up with itself. You go ahead and try to do that, and then I am going to explain it. But take your best shot. All right, I hope you've done it. I hope you stopped the video and you tried it. I want to go to the back for a second. Turn your paper over to the back and let's look at what a line of symmetry might look like. So I am going to take a rectangle, this rectangle, and I'm going to call this rectangle ABCD. And I'm going to reflect this rectangle across the line x equals -3. Oops, now that'll work. There we go. I'm reflecting ABCD across the line x equals -3. So in case you have forgotten, this would be the line x equals -3. So what would happen if I reflected this rectangle across that line? Well, I hope what you see is you see that point A would end up over here. Now, this would be A prime. And point B, 1, 2, 3, 1, 2, 3, would end up here. This would be B prime. And C would move over to D, and D would move over to C, and I would end up with the same rectangle, right? That x equals -3 is a line of symmetry because it makes the rectangle end up in the exact same place. There would also be a line of symmetry, of course, right here. Right? That would be the line 1, 2, 3, 4. The line y equals 4 would be a line of symmetry for that rectangle. You want to see the biggest mistake people make? The biggest mistake people make, well, there's 2 of them. With the rectangle, they try to connect corner to corner and believe that is a line of symmetry. And I can prove to you it's not. One way to do that would be to take your page of notes and try to take the diagonal corners, right, and match them up with each other and see if you can fold the piece of paper I guess I should be over here, huh? See if you can fold the piece of paper and get it to match up with itself. You can't do it. You can't fold the diagonal corners and match up with itself. Down the diagonal is not a line of symmetry. And I just wanted to show you one more thing, and then we will move back to the notes again. So let me see here. What if I did a parallelogram? Let's make a parallelogram down here. We'll go down 4 over 1. Boom. So this is going to be a parallelogram. And people try to do the same thing with a parallelogram. They try to fold it diagonally. And let me show you how that does not work. Let me take the green again. So is this a line of symmetry? That is the question. Is that green line a line of symmetry? I'm not sure this is going to be that easy to understand, but I think it's a good exercise. So that green line has a slope of 1, 2, 3, 4, 1, 2, 3. That green line has a slope of 4/3, up 4 over 3. So if I want to take this point, here, and I want to fold it across that line, I want to reflect it across that line. To reflect it across that line, I need to go perpendicular to the line, right? Remember that from reflections? Perpendicular to the line. So I need to go, instead of 4 over 3, I need to go down 3 over 4. 1, 2, 3, 1, 2, 3, 4. And it would end up here. Let's see. Down, it would be this. Not a great example. It's too close to the corner. But this would be the line of reflection. And this line of reflection, when I fold this over, it does not hit that point. I should have made the parallelogram bigger to prove this. Bottom line is, the parallelogram cannot be folded diagonally, just like the rectangle could not be folded diagonally. And no line of reflection there. Let's go back to the front and see what you did. I'm going to draw these in for you. This one does not have any. We'll do that. The scalene right triangle does not have any, but the isosceles triangle does right down the middle there. The kite does right down the middle. The rectangle has a couple. The trapezoid, out of luck. The isosceles, right? Do you know what it means to be isosceles? Isosceles means at least 2 equal sides. The isosceles does, right? These sides are equal to each other. Same with the isosceles triangle. Those sides are equal. Equilateral triangle means all 3 sides are equal, and it actually has 3 lines of symmetry. Regular hexagon. I'm going to talk about regular in a minute. The regular hexagon actually has a whole bunch. Boom. Isosceles again, which means 2 sides equal. These 2 sides are equal. It has 1. The parallelogram does not. The square actually has 4. Bam. Down here, the regular pentagon. Regular, I'll talk about in a second what that means if you don't know. It actually has 5. The circle. Oh my, the circle. Right? The circle actually has infinitely many lines I could draw. A rhombus. Do you guys know what a rhombus is? A rhombus just means all 4 sides are equal to each other. So all 4 sides equal. And a rhombus has 2. And just any general quadrilateral does not have any. So if we were filling in our little chart would look something like this. The scalene triangle does not have reflection symmetry. The scalene right triangle does not have reflection symmetry, but the rest of these do have reflection symmetry. The isosceles triangle had 1, the right triangle had 1, the equilateral had 3, the regular hexagon actually had 6, the regular pentagon had 5, and the circle had infinitely many, or I could use the infinity symbol. The kite has 1, the rectangle has 2, the trapezoid did not have any. The isosceles trapezoid, though, does have 1. The parallelogram does not have any. The square actually has 4. Not sure how this is going to work now. The rhombus has 2. Couldn't do it. Still couldn't do it. Okay, that's messing me up. Boom. And the quadrilateral does not have any. All right. Let me talk about a couple things on the back here, and we're going to be done. First of all, a regular figure. Figures where all sides are the same and all angles are the same are called regular figures. And you at this point should know a couple regular figures. You should know at this point an equilateral triangle, right? That's a triangle where all 3 sides are the same length. That is actually, could be called a regular triangle. However, when it's a triangle, we just call it an equilateral triangle. A square. A square is actually a regular. Do you guys know what I'm going to put here? A regular what? It is a regular quadrilateral. Right? A quadrilateral is just a shape with 4 sides. So nobody would call a square a regular quadrilateral, but that is actually what it is because it's regular because all 4 sides and all 4 angles are equal to each other. But then after this, once you get to five sides and more, 5 sides plus, after that we just call it a regular whatever. A regular, figure, I guess. I don't know what I'm doing there. But for 3 sides and 4 sides, we do have the special names, equilateral, triangle, and square. And for any regular figure, I think this is worth knowing, the number of sides will equal the number of lines of symmetry. It's true. For instance, in the triangle that I drew above, by the way, this works for any odd number of sides, there are 3 lines of symmetry. Right? There's one from here to here, there's one from here to here, and there's one from here to here. Right? You're connecting each vertex with each side, actually technically the midpoint of each side. You get a line of symmetry from each corner to the midpoint of each side. That's when you have an odd number of sides in your regular shape. What if you have an even number of sides? Like say you have we'll just do a square. When you have an even number of sides, come on, baby. Oh my goodness. When you have an even number of sides, you can connect the corners and you connect the sides. So you're doing vertex to vertex, and you're doing the midpoint of each side to the midpoint of each side. But the bottom line is this: the number of sides will equal the number of lines of symmetry. And the last thing I want to do here is the definition of a polygon for you. It's actually a rather involved definition. It is, first of all, it's a two-dimensional figure. So like a box is not a polygon because it is three-dimensional. So no, not a polygon. It is a closed figure. So you can't have like this is not, it's an open figure. So it is not a polygon. It needs 3 or more line segments. All right, there's a lot to unpack there. First of all, it needs 3 line segments. If it only had 2 segments like this, you can't close it up. So it's not going to be a polygon. It takes 3 sides to make a closed figure, and they must be segments. And in math, segments are straight. So like a half circle, this is not a polygon because it curves. So not a polygon. Polygons only have straight sides called segments. And they must be connected end to end. So, for instance, this is not a polygon. I wish I hadn't drawn it quite like that. Let me try that one more time. I think what I meant to do was something like this. Not a polygon because the segments cross. And they are only allowed to be connected end to end. So really what we have here is, right, we have something like this, where all the segments are only connected at their endpoints. Let me see. Each segment is a side of the figure, right? Down here, this would not be a side of the figure, for one thing. And each side only intersects the endpoints of 2 adjacent sides. Adjacent means next to. So you can see in my figure over here, killing me, that each side is connected to 2 sides. So the top of this thing is connected to this side and it's connected to this side, the adjacent sides at its endpoints. And each point of intersection is called a vertex. So the point right here is called a, there we go. It's called a vertex. All right. A lot of words in there, right? I am done. You can work on your homework. I'll see you.